this graph's data is not in there.
Send it in the black screen.
Just grab a different one.
We'll set this one.
Okay, so the data for this one is not in there, so you will not be able to build this graph. However, I've blown it up big enough, okay, that you can see it, so that we can kind of review what we did on Friday. Okay, which is, how do we use y equals mx plus b? Okay, so just quick reminder. Okay, y is the y value of any spot on the line. Okay, but don't confuse that with a point. Okay, these points, okay, you can see that some of them are clearly not centered on the line. Some of them look like they're close, but really, probably none of them are directly on the line. Okay, so when you're using a y value or an x value, it's got to be from the line, not from one of the points that was plotted. Okay, so when I'm calculating a y value, it's the y value of a point on the line. Same with x. Okay, so a spot on the line. Right? M is the slope of the line, so how steep it is. Okay, that's a function of how much y changes over x. Okay, and lastly, b is the y-intercept, and on this graph, the y-intercept is actually a negative number, which means it's down below the origin. Okay, so b is the y-intercept. Okay, is that ringing a bell from Friday? Okay. I would like you guys to see if you can solve questions 1 and 2. Okay, all you need is the equation and whatever information the question gives. Okay, give you a couple minutes to do those, and then we'll go through them together just as a review. Then we're going to look at how we plot data that has multiple sets on the same graph, because that's what we're going to need to do tomorrow. Okay, so anytime we're doing a calculation with a linear graph, this is a linear graph because it makes a best fit line that is straight, okay, not curved or doing something weird. Okay, so it's a straight line, that means a linear function. Okay, if I want to do any calculations with that, I'm going to use the equation for the line. Okay, in this case, the equation for this graph is that y equals 3.85 times x plus negative 0.801. Okay, so this is our slope. Okay, this is x, this is b. All right, everybody with me there so far? Okay, so the first question wants to know, what is the position of the object after 1 minute? Okay, if I'm solving for position, what part of that equation am I solving for?
Y.
Y, because position is on the y-axis. Okay, that's how I can tell, right? That's how I figure out what it is I'm solving for. So I know I'm solving for y, which is nice because I don't have to manipulate the equation. It's already set up to solve for y. Okay, and what do they give me when they say 1 minute?
The x-axis?
They give me the x-axis, because time is on the x-axis. There's only one trick with that value. What is the x-axis unit?
Seconds.
Seconds. What did they give me? Minutes. What do I have to convert it to? Seconds. Okay, it's got to match. My units have to match. So if you didn't do that, you probably got a much different number. About, I don't know, 60 times smaller. Okay, than probably should have been. So if I'm going to do this question, I'm just going to go y equals 3.85 times 60, my x value, plus negative 0.801. Sorry, I forgot to fire up the calculator. Please. All right, so we got 3.85 times 60 minus 0.801. I could say plus negative, but subtracting is the same thing. Okay. All right, so the position of that object will be 230.20 meters. question number 2, it wants to know how long it's going to take. How long is usually time, so what am I going to be looking for? X, yeah, because time is on the x-axis. So we're looking for x, and we know the position, or y, is 150. All right, first thing I've got to do is manipulate this equation to solve for x. So y equals m times x plus b. What do I move first to get x by itself? Take b. Okay. If I want to move b, because b is not attached, I want to do the opposite. What's the opposite of add? Subtract. Okay, so I'm going to go y minus b equals m times x. All right, I want x by itself. I'm multiplying it by m. How do I move m? Divide, right? Do the opposite. Okay, now I'm solving for x. Now I can plug in my numbers. They told me y is 150 minus negative 0.801. That's important. Okay, I subtracted b, but b is a negative number. I have to keep that in play when I move it over. Okay, and I'm dividing that by m, which was 3.85. So in this question, I put in a couple of tricks that come up just so that you get exposed to them. Okay, that's one of them. If b is negative, make sure you bring it over as a negative. Okay, so I'm subtracting a negative number. So I'm going to have 150.801 divided by 3.85. Okay, so it's going to take 39.17 seconds to reach a position of 150 meters. Okay, that ringing a bell from Friday? Okay. How are we feeling about the algebra? Oh, I put meters. I said seconds, didn't I? I don't know why I put meters. Do as I say, not as I do. Something like that. Okay. How's the algebra? Are we okay with that? Okay, because I mean it's not like super tricky algebra, but that's the kind of algebra we're going to be doing all through this unit. Okay, it will get more involved than that as we go along. All right, I want to have a look at the next one, which is a multiple series graph. Okay, so we're going to have data that looks like this. So if we go into our into that file, it's here called multiple run graph. Okay, so we're going to pull up that data, multiple run graph. Okay, and I got to sit down to do this. Okay, so if I want to do a multiple run graph, okay, I'm going to click and drag and highlight all of my data. Same as before, there's just more of it. Okay, one of the things that really helps Google Sheets graph properly is to have proper headings at the top of each column. Okay, then it understands what's in each column, and if it looks similar, okay, its algorithm will say, oh, these things are all similar, so they should go together, and this one should be the x-axis, these ones should be the y. Okay, and it does a pretty good job of that most of the time. Okay, the other thing you have to be mindful of, look at where I put the units. Okay, did I put any units in the boxes with the numbers? That's another thing that Google Sheets doesn't like. Okay, if I put units in here with these numbers, Google doesn't know if it's a number or a letter, and it doesn't know how to graph it. Okay, and it will simply do this. So if I have those in there, okay, and I put like meters, oh, wrong keyboard, meters, okay, meters, whoops. Okay, so if I try and graph this now, that I've got those m's in there, this is what will happen. Okay, it puts them in there and it switches the axes. These are not the way it's supposed to be. Sometimes it'll just say no data. Okay, it'll get so confused, it'll just say no data, and we definitely don't want it to say that. So always make sure when you're building a chart, okay, that you put the units only at the top. Okay, so we're going to click and drag and highlight it all. Okay, then we're going to go insert chart. So follow along with me, guys. You need to build this graph as well. Okay, insert chart. Okay, now it shows a bar graph. Sometimes Google doesn't get it right, and that's okay. Right? We can fix it. So if we go over here to chart setup, okay, right here it says column chart. I don't want it to say column chart. I want a scatter plot. So I click on this, and I simply scroll down, and it's a little ways down below pi, right here. Okay, scatter. Just click on that, and it'll rebuild the graph. Okay. Now, one of the things you'll notice in this graph is that I don't have a label on my y-axis. That happens when you have more than one data set. And so you'll have to manually enter that in a minute. But at least now we've got the right kind of graph, and I can see the points. Okay? Is everybody with me there? To that plot? Okay. So I'm just going to make this bigger so you can kind of see what I'm doing. All right. So I'm going to go over to customize now because I got to fix my graph. Okay. The chart axis and titles is probably the first thing that I should change. You can do that in two ways. You can click here in title text, or you can just go directly here and you can not move it. You can just type it in yourself. I would say that title is not very good. Okay, that does not really tell me what is on that graph. I would call this a position versus time graph. Okay, and right now, here in chart title, okay, if I click on that, I need to put in a vertical axis title because it doesn't have one. Okay, it has the numbers there, but there's no title. So if I click on that, you'll see that here it says vertical axis title and it's blank. Just go in there and we put on that one position in meters. Okay, so you can see as I type it, it shows up on the left-hand side of the graph right here. Okay, so my graph is shaping up. It's a lot better now than it was a minute ago. Okay. From there, I can close up that now. And I want to go to series. Let me know if I'm going too fast, guys. Okay, so go to series, and you definitely want to have this applied right here. It usually is by default. It says apply to all series. So that means everything I do, it's going to do for all three of the data sets. Okay, so for the yellow, the red, and the blue. Okay, so I'm going to change the point size down to 2. Okay, make it a bit smaller, and I am going to add a trend line. So I'm going to click that box just like we did the last time. Okay, for all of our other ones, click on trend line. Okay, now I've got a line for each graph, or for each data set. And then I want to put in the equation. So I need to go down here to label. Currently there's no label. Click on that, use equation. Now you'll see that it probably will move the legend over to the right side, and that's fine. Okay, but now there's an equation for each line. Okay. Everybody with me there? All right. So now our graph is good. Okay, so we got a graph. It looks pretty much like this. Okay, and we've got our equation for each line. Now, before we get into the questions, okay, we kind of need to talk about what this graph shows. Now, we've talked about what displacement is. Okay, we know that displacement is our change in what? Position. Okay, so does this graph, does it give us the ability to calculate an object's displacement? It does. Okay, an object's displacement is its change in position. Okay, I could calculate the final position of the object. I would know its initial position because it's actually on the graph. specifically, it's in the equation. What part of the equation tells me the initial position of the object?
B.
B. Okay, because what is B? B is the y-intercept, okay? And the y-intercept is what is the value of y, the position, at time 0. Okay, so the initial position is B. So for cart 1, it's 9.52 times 10 to the minus 3. That's 0.00952 meters. Okay, and for cart number 2, it's actually a negative value. It's negative 0.0524 meters. And for cart 3, it's 0.0381 meters. All right, so each cart is just a little bit behind the other. Okay, they couldn't all be at the same position, or they'd be right on top of each other. Okay, everyone follow me on that? So I know the initial position. I could calculate the final position. I could calculate the displacement. Okay. I can also get the velocity off of this graph. Okay. What's our formula for velocity? How do we calculate velocity?
Displacement divided by time?
The displacement divided by the time. Okay, now we were just saying that displacement is the change in position, yes? Okay, so could I say that the change in position would be my last y value, my final position, minus my initial position? Would that be okay? I mean, that's what's true, right? My final position would be my last y value, so I'd call it y. Okay, b, we've already said, is my initial position. Okay, and divided by time. Time is on the x-axis. What's missing there? What does that equal? What does y minus b divided by x equal? M. So what does that mean the slope of this graph equals? It means it equals velocity. Okay? Almost all of the formulas we're going to use are actually derivations of y equals mx plus b. So they're learned, essentially, from a graph. Okay? In this case, the velocity of an object is equal to the slope of its position versus time graph. That's what our lab tomorrow is going to be about. We're going to get several sets of data by running some carts down the hallway, and we're going to graph them, and we're going to calculate using the graph their velocities. Okay. Everybody with me so far? So can we do question number 1 right now pretty easily without any calculating? Okay, what's the velocity for cart number 1? 1.38, right? Because this is m. That's the slope for cart 1. So cart 1 is moving at 1.38 meters per second. Cart 2 is moving at 2.01 meters per second. And cart number 3 is moving at 3.39 meters per second. Okay? Everybody all right with that? Okay. I would like you guys to do questions 2 and 3. So you're finding the position of each cart. So it's 3 calculations. Okay? The position of each cart after 12 seconds, and how long it will take each cart to reach a position of 50 meters. Okay? Sorry, I forgot to record that. There's the answers. The first thing we need to do is we have to manipulate y equals mx plus b, okay, so that it solves for x, because that's what number 3 is asking us to find. So we're going to first subtract b from both sides. So we'll have y minus b equals m times x, and then we'll divide both sides by m, and that'll leave us with x. Okay, so we're going to do that calculation 3 times, 1 for each cart. All right, so if we're looking at the first cart, okay, x is going to equal 50 meters, because that's what they told us y is, minus 0.00952. That's our b. and then we're going to divide that by m, which is 1.38 for the blue card. All right, so 50 minus 0.00952, and I have to do that calculation first and then divide by 1.38, otherwise I get a different answer. Okay, that's going to be 36.22 seconds. Okay, you need to do the same thing for the red cart. Okay, so for the red cart, I still am going to have 50 for y. I'm going to put in the y-intercept b for the red cart. That's negative 0.0524. And then I'm going to divide that by 2.01. And that'll give me the time it takes the next cart. Should that be a bigger number or a smaller number? It should be smaller. This is a faster cart. It should take less time to reach a position of 50 meters. Okay, so 50 minus negative 0.0524 divided by 2.01. Okay, so we got 24.9 seconds, which is slow, which is smaller. Okay, and then lastly, calculating x for the yellow one, we're going to have 50 minus 0.0381, okay, divided by 3.39, and that should give us an even smaller time because this cart is even faster. And so 50 minus 0.0381 divided by 14.74. Okay, that is exactly what we're going to be doing with our lab tomorrow. All right, questions on any of those? So, for today, guys, we're going to go over position versus time graphs because that's what our lab tomorrow is going to be about. Okay, so the key points for today, we need to understand what information can be read specifically today from position versus time graphs, but we will be talking about velocity versus time graphs as well. Okay, understand that graphs and equations from kinematics show the same information in different ways. That's that whole thing I did with the slope being equal to the velocity, okay, on that graph that we were using just a few minutes ago. Okay, that b equals d over t formula that we use is actually derived from a position versus time graph, and that's where it comes from. Okay, and that's the last point there. Okay, so if I've got these position versus time graphs, okay, are they showing different types of motion? They don't look at all alike, do they? Okay? They're definitely showing different kinds of motion. One of the things you're going to be required to do is to be able to look at a graph and tell me what is happening on that graph. That is, interpret the graph. That doesn't require you to do any math. It just requires you to be able to look at the graph and understand what's going on. So on this first graph here on the left, okay, we have position in meters on the y, okay, and we have time in seconds on the x. Now, what is going on for the first second of this graph? In other words, for this section of the graph, what's going on? Nothing. The object is standing still at a position of 20 meters. Okay? The line is flat. That means there's no change in position for 1 second. Okay? That's good. All right. What's going on between 1 and 3 seconds?
Movement to 40 and 60 meters.
Okay, movement between 20 and 60 meters. Okay, so that would be one way of looking at it. Okay, I would say if this was a 3-mark question, that would be one of the things I would be looking for. Okay, it's moving from 20 to 60 meters. It's moving, is it moving accelerating, moving at a constant velocity? What do you think? it is moving at a constant velocity. Okay, here's how we can tell. Between 1 and 2 seconds, it goes 20 meters. In the next second, it also goes 20 meters. That means each second it's going 20 meters. In other words, it's traveling at a constant velocity of 20 meters per second. And I said velocity because it's also moving up, forward, in a positive direction. Okay? It's not like slanted down like the last section is. Okay? So if I was looking for 3 marks worth of stuff for that, I would be looking at moving forwards from a position of 20 meters to 40 meters at a constant velocity of 20 meters per second. Okay? That would be a 3-mark answer. Everybody follow the interpretation there? Okay? What's going on between 3 and 4.5 seconds? Nothing. Okay? The object is sitting still at a position of 60 meters, positive 60 meters. Okay? What's going on between 4.5 and 6 seconds?
Just going down.
It's going down. Okay? From 60 to 20 meters at. Is it accelerating or going at a constant velocity?
Constant velocity.
It's constant velocity. The line's straight. That means its rate of change stays the same. Okay? The graph on the right, that's showing an accelerating object. Okay? This is showing an object traveling at a constant velocity backwards. Could I calculate that velocity? I could, okay? Because we know that velocity is displacement divided by time. In other words, our change in position. So how much does our position change by if we go from 60 to 20? 40. Yeah. But it's negative because it goes backwards. Okay? So if I was actually calculating this, I would say my final position minus my initial position divided by time. In other words, I'm actually finding kind of the slope of that part of the line. Okay, so my final position is 20. My initial position is 60. And that takes 1.5 seconds. So 26.7, but it'd be negative. Negative 26.7 meters per second. Okay, am I just using stuff from our formula sheet? Okay. Could this have been one of the questions you would have got when we were just working on like 2-part V equals DT problems? It absolutely is. It would have sounded something like this. Okay, a bus is parked at a bus stop for 1 second. It then travels from a position of 20 meters to a position of 60 meters over the next 2 seconds. It then stops at the next stop for 1.5 seconds. And then, but you better get on this bus fast because it only stops for like a second or 1.5 seconds. So you gotta like jump on. Okay? And then it turns around and goes back from 60 to 20, or from the last stop to the first stop. Calculate its total displacement. Okay. Can I calculate its total displacement? Do I need to do any math? Not really. What's the total displacement? 0, right? We started at a position of 20 meters. We ended at the same place. That means the total displacement is 0. Okay. Could I calculate the total distance? Does distance care whether I go forward or backward? It doesn't. Okay. So, how far do we go here? What's the distance traveled in this part?
20 meters.
That's our position. How far do we go? 0. We don't go anywhere, right? The final position here and the initial position here are the same number. So we didn't travel. You guys told me when I asked what's going on here, you said nothing. Okay, well, if nothing's going on, then I also didn't go anywhere. Okay, my distance traveled there would be 0. What's my distance traveled from here to here? I go from 20 meters to 60 meters. How far did I go?
40 meters.
40 meters. How far do I go here? I don't go anywhere. Okay, and I go here, I go from 40, or from 60 to 20, which is? What's my total distance traveled? 80 meters. Okay, 40 plus 40, because again, distance is scalar. Doesn't care that I went backwards. Okay, but this is also why our displacement is 0. We went 40 meters forward and 40 meters backwards. That means we end up back where we started. Okay? All right, here's one that should take you 2 seconds to get. What's my average velocity over the whole trip? Zero. Okay, why is my average velocity 0? Because average velocity is total displacement divided by total time, and you guys just told me my total displacement is 0 meters. Which means it doesn't matter how long it takes, I didn't go anywhere, so my velocity would be 0. Okay, now, this one might take a hair longer. What's my average speed? How far did I go? You guys just told me this a minute ago. How far did I go? 80 meters. How long did that take? 6 seconds. Looks like I'm going 13.3 meters per second. Okay, so graphs are just showing us the same kind of thing that those word problems were telling us. It's just faster, because I don't have to write down part 1, part 2, and calculate all the stuff for part 1 and part 2. I can just read it right off the graph, and it takes way less time. Okay, that's why graphs are handy. All right, questions on what we did right there? That stuff would be like multiple choice question, maybe written response kind of stuff, okay? But you've got to be able to interpret a graph. Tell me, okay, it's moving at a constant velocity. It's not going anywhere. It's moving at a constant velocity backwards. What's its total displacement? Things like that. All right, now our other graph here. This graph shows an object whose speed is changing. Okay? In other words, this object is accelerating. Okay? In this graph, when the object was traveling at a constant speed, the line went up and over the same amount every second. Okay? So that meant it was changing its position by the same amount. In this graph, that's not happening. In the first second, the object goes this far. In the second second, the object goes that far. In the second after that, the object goes that far. In the second after that, the object goes this far. And after that, that far. Is that vertical line getting longer each second? Well, the only way you go farther in the same amount of time is if you're going faster. In other words, this object is accelerating. It is going faster and faster and faster. Okay? Because its change in position gets larger each second. Okay? So that would be something I would also expect you to be able to read from a graph. Look at that graph and go, oh, each second it went farther than it did the second before. Only way that can happen is if it's going faster. That object's accelerating. Boom, got my answer. Okay? That's interpreting a graph. Doesn't require me to do any math, just requires me to be able to look at a graph and know what's going on. Okay? We call this kind of change exponential growth. Okay? If this is like the value of stocks, this is good, because that means your stocks are worth way more money all the time. Is that good? Yeah. What if your graph looks like this? That's bad, especially if it's money, okay? Because now your stocks are worth less and less and less, like Twitter. I don't think that's pay attention to news, but that's like tanking big time, okay? Or crypto, same thing.
Yeah, they let Trump back on Twitter.
Yeah, well, I don't have a comment about that. Okay, does that make sense? All right, so when we do a slope calculation, okay, because we were talking about slope here a little while ago when we were doing the linear graph, okay? The slope tells us the rate at which y changes as a function of x, okay? So when we get the equation for the line, okay, m is our slope, okay? It's the rate of change of y as a function of x. So I can calculate it by manipulating this equation, which we've done already before. If I want to solve for m, what do I do with b? Subtract it. Okay, and I want to get m by itself, so what do we do with x?
Divide.
Divide it. Okay, so now I'm solving for m. Does that look y minus b, because remember, this would be I'm just going to extend that line, go all the way to the y-axis here. So this would be b right here, okay? This would be m, and then obviously this would be x, okay? So when we say y minus b over x, is that the same as doing this? Change in y divided by the change in x. Is it the same thing? It is. Okay, so there's more than one way to calculate slope. Okay, we in physics typically use the second way, y minus b over x is m. Okay, and the reason for that is that formula is a bit more useful. Okay, in terms of calculating things other than slope. Okay, rise over run is good for getting slope, but not much else. Okay. All right, everybody okay with that? Because we've already done that slope stuff, just kind of reviewing it there. Okay, if this, okay, so this is a displacement or position versus time graph, right? So any y value represents the object's what? Position. Any x value represents the time. Okay, because that's what's on the x-axis. Okay, so y and x, their values are whatever is on their axis. Okay, b is our what? What's the time at b?
0.5 or 0.5.
0, just 0. B is at 0. Okay? So this is my initial position. It is wherever I am at time 0. It's where I start. B is my initial position. Y will be my final position. X will be my time. That's why when I calculate the slope of this graph, I am actually doing this. And calculating the velocity. Okay, that's something I don't want you to memorize. Okay, that's something I want you to be able to calculate. Is slope always velocity? Like on every, if I take a whole bunch of graphs and I calculate the slope of all those graphs, is that always going to be velocity? Not at all. Okay, it's only velocity on this graph, on a position versus time graph. Okay, if I had a graph that was slope of that line gonna be velocity? Absolutely not. Position and time, which is how I get velocity, are not on this graph. Time is, okay? But the y-axis is the value of shares. Incidentally, don't buy this one. Okay, why? It's going down. It's gonna be 0 pretty soon, okay? That's not something you wanna buy a lot of stock in because it's going down right now, okay? That's why you wanna be able to interpret graphs. That's an important life skill, okay? Like they show graphs on the news all the time, okay, on the weather, whatever, like graphs are important. Being able to read and interpret a graph is meaningful, okay? Because it tells us the trend of something, okay? The slope of this graph would be in dollars per week. Okay? So it's the rate at which the value, well, the rate at which I lose money, really. Okay? That's the slope of this graph. Right? If the graph is going the other way, it would be the rate at which I make money. X many dollars per week. Okay? So the slope is always y over x. Okay, let's do a couple of quick calculations with this graph. Actually, before we do calculations, what's the object doing in part A? Okay, it's a position versus time graph. Let's be a little more specific. You're right, the position is rising at sorry, what? At 3 meters per second, yes. Okay, this is an object traveling at a constant velocity. That's the part I was looking for. Okay, constant velocity of 3 meters per second. Okay, how do we calculate that? We went 6 over 2. Okay, so it's traveling forwards at 6 meters per second. If I was asking that question, that's the answer I'd be looking for. Okay, what's going on in part B? Nothing. The object is standing still. What's going on in part C?
It decreases at a constant velocity?
It decreases at a constant velocity or moves backwards at a constant velocity. Okay? And I would say moves backwards might be a little bit better as opposed to decrease, because decrease implies we would stop at what value?
0?
At 0, because you can't decrease below 0, right? Okay, so in this case we would say traveling backwards at a constant velocity, okay, or changing position from +6 to -10 meters at a constant velocity. Any one of those shows me that you've read the graph and know what's going on. What's going on in part D?
And it stays at the velocity, or it holds velocity.
Yeah, it does hold velocity, but what's its velocity in part D?
-10.
Its position is -10. Its velocity is 0. It's not moving, right? It stays at a position of -10 meters. Totally right. Okay, that means its velocity is also 0. Okay. Where is the object going faster, E or F?
E.
E. How do you know?
It's a sharper slope. Or
Steeper slope, because slope on this graph represents
speed.
speed or velocity. Okay, and if it's steeper, it's faster. Okay, did that require us to do much math? Just requires us to know, okay, this graph is showing me where the object is at various points in time, and thus how it's moving between those positions. Okay, another simple calculation. What's the total displacement of this object? Somebody whispered it. 0. How do you know?
Because it started and ended at the same place.
Exactly, it started at 0 and ended at 0. Final position and initial position are the same place. Okay, what's its average velocity over the whole trip? 0, because its displacement is 0. All right, this one might take a little bit longer. What's the total distance traveled? This you have to do piece by piece. Total distance, 32 meters. How'd you do that?
I just counted up 6, 6, 10, and 10.
Right. went 6 meters here, went 6 meters here, went 10 meters here, and then went from negative 10 to 0, that's another 10 meters. 10 plus 10 is 20, plus 12 is 32. Okay, assuming this whole trip takes 18 seconds, we'll just say it ends here. Okay, what's the object's speed?
0.
The velocity would be 0. It's not quite 2. It's a little less than 2. What did you guys just tell me the distance was? And I just told you the time is?
1.7
Okay, V equals d over t, right? That's total distance over total time. This is just like those word problems we did. It's just a graph instead. Okay? All right, we will leave it there for today. We're going to be doing the lab tomorrow. And a quiz. I'll post it. It might have a simple graph and a v equals d over t problem. Probably.